Chapter 10 deals with rotational motion and angular momentum. There are things that rotate all around us in the world. The wheels on our vehicles, the discs in our DVD player, centrifuges in labs, fan blades in jet engines. Even the Earth itself is rotating on its axis. We've previously analyzed objects moving in a circular path and derived the equation for centripetal acceleration, but this chapter deals with rotating objects. Figure 1011 shows an example of circular motion. Here a mass is attached to a string and it is being pushed around a circular path on a frictionless table. We'll come back to this situation a little later and use it to help us understand the concept of moment of inertia. But in this chapter we're studying the behavior of rotating objects, rigid bodies that rotate about an axis. It may be the tray inside your microwave, or a merry-go-round at the park, or a wheel on your bicycle. Let's begin by defining some terms. In some math class you were introduced to the idea of measuring angles in units of radians. The measure of an angle in radians is the ratio of the arc length to the radius. We can rearrange this equation to show that the distance traveled along an arc of the circle is equal to the radius times the change in angle. Similar to how velocity is change in position per time, we define the angular velocity omega as the change in angular position per time. Let's go back to the example of the mass going around a circular path. As the mass moves around the circle, in a time delta t, the mass will move along an arc of the circle a distance delta s. The string attached to the mass moves through an angle delta theta. Since delta s over delta t is speed v, and delta theta over delta t is omega, we have this relationship between the speed of the mass and its angular velocity. In a similar way, the angular acceleration is defined as the change in angular velocity per time. If the mass is speeding up or slowing down, its speed is changing, and the change in speed over the change in time is translational acceleration. This gives us acceleration is equal to r times alpha. These three equations relate the translational quantities of distance, velocity, and acceleration to their rotational analogs of angular displacement, angular velocity, and angular acceleration.